All right, welcome to example number 2. This is a little bit more challenging than the earlier example because it's going to involve several topics. I've included into this problem an extra little bit actually. So this boy is whirling a stone in a horizontal circle. So this is actually a view, like a top view here. And then the stone breaks and then it flies through the air and it's going to look like projectile motion, which I'll get into a little bit later. But my first question to you is, when this stone breaks and the string snaps right there, what direction is this stone going to go? Is it going to go like in a straight line path? Is it going to go around this curved path? Is it going to go maybe around that path or straight outwards? Which one do you think it's going to go through? Do you think which of these paths do you think you have? So think about it carefully. All right. I get a lot of people that choose A because you can think, well, the ball's just going to keep going around a circle because after all, it was going in a circle. Some people will be choosing D because, you know, it breaks and this feels this outward force and it goes straight out. Or maybe it's some combination of B and D and it's like C where it feels a force but then it wants to go in a straight line. And then there's B, which is basically the rope. I mean, after all, at that particular point, the velocity is this direction. So when it snaps, then naturally the ball would just want to continue in the same state of motion. That's a little bit hard to discuss at this point in the course because we haven't really discussed forces yet. We haven't talked about inertia. But maybe I'll just give it a very quick intro and just say that an object at rest will remain at rest. An object in motion will continue in motion, in the same straight line motion that it was going. So at this particular point when that stone breaks, the stone is actually just going to keep going in a straight line. And this is due to the fact that all objects have inertia and they want to just continue in that same state of motion. So the answer actually is B. It's not A, C, or D. I'll show you a demonstration in class. Okay, well, let's get on to the problem here. We need to find the centripetal acceleration. So let me write down some given information here. We have the radius of the circle is 1.5 meters, so this R is 1.5 meters. We have it travels a horizontal distance of 10 meters, all right? And it is a vertical height of 2 meters. So we'll put that as like Y initial. All right, so a lot of information here. We're trying to find the centripetal acceleration. So my first approach I'm thinking here is, well, we're trying to find the centripetal acceleration, so I'm going to use the formula AC equals V squared over R. Now, the problem I have right now is I do know the radius, but I don't know the speed. The speed is not known, so I need to find that value here. Okay, so how can I get that? And you might be thinking, well, the speed is equal to 2 pi r divided by t. And you're like, I got the radius, but again, the problem is I don't know t. So that's not going to work. I'm not told enough information about how many cycles it makes per minute or whatever it is. I don't have that information. So unfortunately, I cannot use this equation. It's not going to work. I need to find the velocity in another method. Now, if you kind of visualize this in a different way here, and let's say this is the ground, and the stone is getting, you know, this is like now a side view, let's say. That was the top view that I was drawing. So the boy was like standing here, and the stone breaks off from that horizontal circle here, and it now is moving horizontally like that. And so then the stone is now going to follow a projectile motion path. And we have it landing a distance of 10 meters horizontally, and it started a vertical height of 2 meters. All right, so this is a projectile motion problem mixed in with a uniform circular motion problem. Lovely. All right, so we're going to put down our axes in here. Let me just make it like red or something here. And so I'm going to put an axis right along the ground here. Okay, let me make that again. So here we go. And then we're going to do a vertical axis there. So I'm just picking up my coordinate system. All right, I'm choosing this to be my origin. So therefore my original position is 2 meters. And when the ball gets down to over here, the vertical position is going to be 0. So I've got a few more little given pieces of information. I know that y final is 0 meters. And I also know that it accelerates vertically at negative 9.8 meters per second squared. Furthermore, I know that the initial vertical velocity, because when it's fired off here, that v is really just v0x. The v0y initially is 0. It doesn't have any initial vertical velocity because it's being moving in a horizontal circle, so therefore it's got to have no initial vertical velocity. So we need to find this horizontal velocity, which represents the velocity of the stone when it's snapped. But in order to do that, if you look carefully, I have a lot of vertical information. I know the initial position vertically, the final position, the acceleration, and I know the initial vertical velocity is 0. So before I can find that velocity, I have to find the time in the air. So we're going to use our kinematics equation, y equals y0 plus v0yt plus 1/2 ayt squared. My final position vertically is 0. I started at a height of 2 meters. My vertical velocity initially is 0. All right, and I have an acceleration of negative 9.8 meters per second squared times t squared. So t is going to be the square root of 2 times 2 divided by 9.8. That gives me an answer of 0.639 seconds approximately. So now that I know that time in the air, well, it goes from here. Now, notice, by the way, this is not the period that the thing goes around, like that t. It's the time that the thing is flying through the air when it gets snapped until it hits the ground. So now what we're going to do is we're going to find out that speed here. So if you recall, horizontally, x equals x initial plus v0xt. Let's throw in this term as well, but we know that the acceleration horizontally is 0. There's no air resistance, so it's only accelerating vertically. So this term goes to 0. We'll assume that the initial position horizontally is 0, and so we end up with x equals v0x times t. Now it moves 10 meters. So it moves 10 meters. Then the initial velocity in the x direction multiplied by the time of 0.639 seconds. So then we can find out the speed in the horizontal direction. Keeping all my digits from my calculator, I get an answer of 15.65, we'll say, meters per second. And so now the last piece I need to do is use that in our centripetal acceleration equation. So centripetal acceleration equation is v squared over r. And so we've got 15.65 meters per second, that quantity squared, divided by the radius of my circle, which was 1.5 meters. All right. And I get an answer of 163 meters per second squared. And there you go. All right, and that's it for this example.